Hello guys, in this lesson we're gonna start to writing a transfer function and state space representation of the wheel model in system dynamics perspective. Okay, in the previous lesson we have obtained the x dot dot times some constants in here must equal to what? The torque value, which is the dynamic equation or the equation of motion of our wheel model. Okay, and so in this lesson we will try to cover up the full picture of the transfer function of our methods. Okay, and so firstly our dynamic is what is the x dot dot times some constants in here m r plus j divided by r is equal to torque. Okay, and so this is the input value of our system, and so x is the dependent of the time, and so this is the output value of our system. And so in the transfer function method we define the input signal to any system which is represented by the GS as a plant model in transfer function. Okay, and so we have obtained the output value of our system, and so in our system dynamic model the XS is the output, is the torque, S is the input variable of our representation. Okay, and so in order to create a transfer function parameter in here, and so this is the in organized form x dot dot must be equal to what? Torque times 1 divided by m times r plus j divided by r. This is our representation. Okay, and so if we organize this formula, and then x dot dot must be equal to torque times r is given in here, and so r divided by m r square plus j must be given in here, and so this is the specific formula to represent the analog parameters like the mass parameter or the spring or the damping ratio. In our case this is the mass parameter in the analogy modeling. Don't forget that this is not equal to the mass, but in the same analogy it means that this term preserve the energy in our system, and so in our system there is no energy form to be stored or to be lost, because in this case the mass preserve the whole the energy according to the Newton's idea. And so what about the transfer function? Transfer function is for this system s square times xs must be equal to s times r divided by m times r square plus j. Okay, this is our representation form. Okay, and so what about the GS? GS is equal to the output divided by the input in time. Okay, and so xs divided by s can be obtained by using this formula, and so the s is the left hand side, and so s square must be given in here, and then the r divided by s square times m r square plus j. This is our transfer function of the wheel system. Okay, and so what about the state space representation in our system. The main formula was given by this dynamics, and so we must write it down in the same region in here, and so this is easy. And so we have the x dot dot times m r plus j divided by r is equal to the TL. Okay, and so in state space representation we need to assume that there is any dummy variable can be assigned to state parameters, like this one. X is equal to the z1, and so z2 can be considered as the x dot, and so z1 dot, or the derivative of the z1, is equal to the what? z2. Okay, and so z2 dot is equal to the what? The z2 dot is equal to the x dot dot, and so torque times r divided by, this is the general notation, and so m r square plus j. Okay, and so in the state space representation we should write the z dot times az plus b tau. Tau is the input variable, and so z is a vector which is represented by the x and x dot. And so if we write it down as the z1 dot times z2 dot is equal to some matrices times z vector in here, z1 z2, plus some b vector in here times torque value. And so how can we create the A matrices? A matrices includes the both two derivative terms dynamics. Okay, for example, z1 dot can be, it consists of the z2 only, and so z1 is not a parameter of these things, and so we need to write it down as the serial, and so z2 is included in the z1 dynamics, and so the 1 should be written in here. And so z1 dot does not include the torque value, and so we need to put the 0 in this term. Okay, and so z2 dot has, or the z2 dot has no parameter with the z1 or z2, and so 0 0 must be written at this position, and so the torque value is included in here, and then the dynamic coefficient of these things m r square plus j. This is the our main representation of dynamics in the state space representation. Okay, SS form of wheel model can be given by this notation or these matrices systems. Okay, and so in the next lesson we will discuss about how can we add the braking system analogy to this notation, because in our system there is only mass parameter in the analog form, and so we need to add the brake mechanism like the ABC. Okay, in the real life application. And so if we are creating a braking system analogy in here, and then we should proceed the following stage like this one, the whole the dynamics rewritten in the form of including what? The damping ratio of these wheel techniques. Okay, and so in the next lesson we will discuss about it.